Namaste, chemistry students of the world. And here we are, Pass Mark Chemistry, where we go through all the answers of chemistry to help you pass your assessments. So, um, we've had a request from one of the subscribers in the last video. They've said they wanted a video on how atomic radius changes across the periodic table. So I thought, let's talk about the periodic table today. So thank you, Hussein, for your question, your request. Let's get into it. So the periodic table looks a little bit like this. If you're a chemistry student, you'll be pretty familiar with it. It was Dmitry Mendeleev, the Russian scientist, who first came up with the original periodic table. And he says that he dreamt it. He saw the whole thing in his dream, which I don't believe. I think he's lying because people don't dream in tables, do they? Well, maybe Dmitry Mendeleev did. Now, his original periodic table didn't look like this. It didn't quite have the same structure and detailed layout, but he came up with the first concept of arranging all the elements we knew so that they would go in groups of reactivity. So down the way is our groups of reactivity, and they're ordered sort of along the way in rows or periods. The periods of a periodic table are the rows is the size. So going across this second period here, lithium to beryllium to boron to carbon is going from 3 to 4 to 5 to 6. It's increasing in atomic number. So they're getting a higher atomic number as it goes across the period. But does that mean that it gets bigger? Well, the nucleus is getting bigger because the atomic number, the 3, 4, 5, 6, 7, 4, my different elements going across the way, means that I'm adding more and more protons. And when I add more protons, I need more neutrons in that nucleus to fill the thing in. Inside my nucleus, going from one proton to two protons, I'll probably need a neutron to hold them together, or at least two neutrons maybe. Uh, and then I get an extra proton and then another proton. So my nucleus gets bigger with protons with their positive charge and the neutrons of a neutral charge. They're like the atomic glue holding the whole nucleus together. And then, of course, you've got your electrons going around the outside. Now, it's hard to draw electrons. For the most part, we like to draw them in nice, neat circles, but that's not really what the electrons are doing. Their path is a little bit more random than that. But they do have sort of energy levels, so the easiest way to draw on a flat page, rather than drawing a sort of mad three-dimensional squiggly line like I've just made a mess here, is we'll draw them in circles whenever we draw elements, not because they're going round and round in a circle necessarily, but they do have an energy level that means that somewhere within this three-dimensional shape it's going to be going kind of round it. Um, so my protons in my nucleus, my neutrons, and as I go across my periodic table, my nucleus gets bigger. So again, those first few elements, my lithium, atomic number 3, beryllium 4, and then over here I've got the boron 5, carbon 6, nitrogen 7, oxygen 8, fluorine 9, neon on 10. So this is a full period that I've drawn out here. And as we can see, we're adding that atomic number 3, 4, 5 means I'm getting more and more protons as I go across. So I'm adding an extra proton each time, and that's what makes it a different element. The number of protons the element has is its identity. So as long as I have 4 protons, I'm always going to be beryllium. If I manage to somehow gain an extra proton, then I change the element that I am. Now, this sort of thing can happen in a nuclear reactor, but it doesn't really happen naturally very often unless you've got very big radioactive elements that do change. So what can happen is you can change your number of electrons. So to become more or less stable, my elements will either lose or gain electrons to try and become more stable. Now the number of protons is going to stay the same. So take a nice easy example for me. Lithium has, say, 3 protons, and let's just give it 3 neutrons. Now, the truth is that it'll have different number of neutrons depending on what isotope of lithium you have. And just a quick jargon check, an isotope is if I have a different version of the same element. So it's all still lithium, still got 3 protons, but some of them will have more neutrons and some of them will have less, and they're all isotopes of each other. So I've got my lithium here, and my lithium has 3 electrons. The number of electrons is always going to balance out the number of protons that you've got. So 3 protons must mean I have 3 electrons. So my 3 electrons. So I've got 2 there, and then it's got to take an extra energy level to get that third one. The first energy level can only fit 2. It's the smallest one. It's closest to the nucleus. One of the ways that I like to think of my energy levels for my electrons is kind of like seats on a bus, is that they are, for the most part, a maximum of 8, around 8 seats available. But electrons, they don't want to sit next to each other. Just like if you were getting onto a bus and all the benches were empty, and you sit down on a bench, just probably somewhere close to the front so you don't have to walk too far. And then the next person that comes on, they're not going to sit right down next to you if there was all those other empty seats. That would be very strange. So instead, they're going to find another empty bench, maybe another one fairly close to the front, because like you, they don't want to move too far back, but not the seat directly next to you, because you're a stranger and that would be strange. So they'll fill up that seat, and then the next person's going to come on and fill another one seat in the bench, and another one, another one, another one, another one. And it's only when all the other benches are filled with at least one person, the next person who comes on the bus has to go, oh, I've got to sit next to a stranger. But it's okay then. There's no other seats. They've got no other option. They're going to sit down next to you. And electrons are the same. They are not going to sit next to one another if there is an extra available seat. So how we show this in a diagram is this kind of arrangement where my electrons are going to fill up my empty seats before they start adding together, before they go, okay, all right, I've got to sit down next to somebody else before you go, oh, all seats are filled, you've got to go upstairs. It's a double-decker bus, and they've got to go upstairs to the next empty seat. So, let me go back a bit. We have our lithium here. Lithium's only got 3 electrons. So that first row, the first floor of the bus, only has 2 seats. It's really just tight and small, close to the nucleus, and that's also the reason why in our periodic table, the first period, the first row, only has 2 elements, hydrogen and helium, because I fill in 1 seat, fill in 2 seats, and then, oh, I need a new row, a new period. So the next third element, lithium, it has its third electron has to go upstairs to fill in this free seat here. So it's got its 3 electrons. And the idea of electron arrangements is they're all trying to fill all their seats. All elements want to be stable. Everything is looking for stability, even us. We want to feel secure and stable and ready for our exams. So that's why we're watching this video. So they want to feel stable. So for some elements, the easiest way to fill all their seats is not to try and gain all the extra electrons that would fill up the seats. Like lithium here would have to fill another 1, 2, 3, 4, 5, 6, 7 extra electrons. So it's kind of hard to find that many electrons. But here's an idea. It could just get rid of this one outer electron, and then it's only got 2, but it has a filled shell of electrons. It would be equivalent to this helium. Helium's really, really stable. Helium is in this group of very, very stable elements we call the noble gases. They are the group 0. They all end in 8 apart from helium. The reason helium doesn't end in 8 is because it's only got the little layer to fill. All the other elements have 8 electrons to fill around the outside. So my lithium could become stable if it just lost that one electron. Of course, now it's got more protons, positive protons, than negative electrons. It's got one more positive. So it becomes an ion, a positive ion. So I'm going to get my positive ions formed if it's easier for the element to lose electrons to become stable, to fill their shell and reach that point where, nope, it doesn't want to lose any electrons, it doesn't want to gain any, so it's not going to react. And that's what it wants to do, not react. So it's nice and filled shell, it's complete, but it does have this charge now. So my lithium. And the same is going to happen for beryllium. Beryllium's got 4, so it means it's going to have 2 electrons on the outside, an extra proton as well. And it's not going to be quite as
eager to react as a lithium. Lithium is a very reactive element because it only needs to get rid of one electron. My beryllium has to get rid of two, but it could do that. It could get rid of these two, and then, like the lithium ion before it, it gets rid of these two, and now it's got a complete shell. And my beryllium, because it lost two electrons, it now has two more positives than negatives. So it's a 2 plus ion. So my 2 plus ion is now, again, stable. So nice and stable. My elements further on this side. So once I get kind of beyond carbon, so carbon is in group 4. So 4 is halfway between 0 and 8. And 8 is kind of that magic number where the noble gases are going to stay. So once I get sort of beyond 4, let's take nitrogen, for example. Nitrogen, and I'm not going to bother drawing all the protons, but we know that inside here, inside the nucleus, it's got its um, 7 protons. How many electrons has it got? Well, it's got the 2 in that inner shell, and then it's got its 5. So 1, 2, 3, 4, 5. So 5 outer electrons. So losing 5 electrons is what it would do if it was following the pattern of the lithium and beryllium before. But actually, this nitrogen could become more stable or become stable faster if it just gained 3. So if it was somehow managed to get 3 electrons from somewhere else, they could fill in these seats, and then it'd have a complete shell of 8. It would be equivalent to a neon, which would be the next noble gas down. My neon with its 8 outer electrons. So that is what the nitrogen wants to do. So that would make my nitrogen stable. 8 outer electrons, filled shell. It's just that it's going to have 3 more electrons, 3 more negative charges than positive charges in the middle now. So again, I've got another ion. So my nitrogen ion. And that's why, depending on what side of that 4, it's easier to lose electrons. On this side, it's easier to gain. So I have a loss of electrons this way, and I am gaining electrons going this way. So if that 4 is in the middle, this is my group 4 where the carbon is, but gaining electrons is easier for the elements on this side. And we can loosely split this up into metals on this side. All metals want to lose electrons, and all my non-metals on this side want to gain electrons. So that's about it trying to become stable. It's always trying to reach 8. It's always trying to gain those electrons to become stable. Now, what's this got to do with our trends in periodic table? Well, it's kind of a little bit about why the periodic table is set out the way that it is, and that idea that they're all trying to look for stability. Now, there is a characteristic, a property, a quality of how much something wants electrons, and this is called electronegativity. Electronegativity, how much it wants electrons. Because some elements want electrons and some want to lose them. And how much you want them is its own quality, electronegativity. In fact, this can even be measured, and elements can have a value for it. Now, the element that has the highest electronegativity, that really, really wants electrons the most, is a fluorine. Fluorine, its atomic number is 9, so it's got 9 protons, 9 electrons. And that 9 electrons is arranged a little bit like this. So my nucleus in the middle that I'm not going to show just because I'm lazy, but my electrons, I've got 2 in the inner shell, and then I've got 7 in the outer shell. And 7 is so close to 8. It just has one last seat to fill. It really, really wants an electron. If I can get one more electron, it could be stable. It could be just like the neon next to it. It's a noble gas and not going to react with anything. So my fluorine is really, really electronegative, which means it's going to be able to pull electrons off from other things. How electronegativity affects bonding is that it means that depending on what you're next to, if you're something more electronegative or less electronegative, then it'll have an effect on how you distribute your electrons. Let me give you an example. So if I had a hydrogen bonding next to a hydrogen, and then if I had a hydrogen bonding next to a fluorine, now in both these cases, I'm forming a bond, and that bond is a sharing of electrons. So if I cannot lose or gain electrons, like I said that they want it to do, they want to become stable, so you lose electrons, you gain electrons, but you become an ion. But you can also kind of cheat the system. If there's no electrons around, but there is other elements, you can say, hey, well, you know what, we could share. We could share our electrons, because if my hydrogen has its one electron, it wants to gain two to become stable, or potentially just lose one. So if to become stable, let's say it really wants that second electron. If it can have two, it could become stable. But no one is willing to give him another electron, this hydrogen. Um, so if it found another hydrogen with its one electron, it says, look, we can stick together. The two of us, if we share our electrons between us, we'll have the two that we both want. We're both hydrogens. We both are interested in having two electrons. So let's share. And that's how you form what you might call a covalent bond. So the two electrons, we're going to sort of draw that in an image where they're sort of overlapping in energy layers, where the two electrons are now being shared. So now this hydrogen gets to kind of live out its life nice and stable, as though it is living with two electrons. And so is this one. Now they're tied together. They're together now, and they've created a molecule of H2 where they're combined, but they get to have the electrons that they want. So it seems like a pretty good arrangement. But back to that idea of electronegativity. So I said that an H next to an H, that works out just fine. They both want to just share these electrons and it's all going great. But what if I had a hydrogen and a fluorine? Now my hydrogen has its one electron and my fluorine, and I'm just going to draw the outside shell now. So we know that there's two on the inside, but there's seven on the outside. One, two, three, four, five, six, seven. So they both want an electron. The hydrogen wants that extra one electron, just like it did in this first case, to get the two. If it could become two, it could become stable. It could be like a helium. So helium is nice and stable, and it's only got two electrons. Whereas my fluorine really wants one more electron too. It wants its one more electron so that it could be like neon with its eight outer electrons. So they could share, couldn't they? They're just like the hydrogen and hydrogen. They could form another one of these covalent bonds, and they could overlap and form a covalent bond. And okay, that works out. My fluorine now gets to have its 8 and the hydrogen gets its 2. But the subtlety comes in this idea of electronegativity because they're not sharing equally. It is not an equal sharing of electrons. So we're saying they're sharing their electrons, but they're not sharing equally because my fluorine just wants it more. The electrons. So when we draw bonds in chemistry, like we just draw them like lines connecting two elements together, is what we really mean is that's two electrons. There's two electrons in any bond. So I'm going to mark them out with a dot. So my two dots on my bond here. Now usually we just draw the line, but I'm showing that it's two electrons here being shared. But my fluorine wants it more. It wants those electrons a little bit more. So those electrons are going to shift a little bit closer to the fluorine than the hydrogen. Now, it's not taken the electron away from it. It's not just removed the electron from the hydrogen. They are still connected. My hydrogen has a connection there. It's still holding on to that electron as well. But my fluorine's just got the bigger share of it. Now, of course, my electrons have a negative charge. And by pulling this electron closer towards itself, it gets a slight negative charge. What I've drawn here is a little Greek symbol. It's a lowercase delta. And all it really means is slight negative. Now, it's not the same as a fluorine ion that's just got an extra electron in there to fill in its outside shell. This is a delta negative, just slight, a slight negative charge. And of course, if this hydrogen over here has almost lost its electron, almost, not completely, it gets a slight positive charge. So a slight positive charge means now I have a negative side and a positive side. What we call this is a polar molecule. So you've probably heard of the North Pole and the South Pole. So if I have a planet, let's call it Earth, I have a North Pole and a South Pole. My two poles, my opposite ends of the planet. And in chemistry, we have poles as well, except our poles aren't north-south, they're usually negative and positive. So a negative pole and a positive pole, a negative side and a positive side to this molecule. One of the ways that we can tell if a molecule is polar or not is that we see this difference in electronegativity, and we see, okay, does it have a negative pole and a positive pole? If we imagine this being split in half, then this is my planet, and yep, this must be the negative pole, this must be the positive pole, or north, south pole, and I have a split. I have a polar molecule. And the fact that it being polar means it's got different properties, and maybe I'll do a whole other video all about polarity another time. But electronegativity has a trend in the periodic table, and that's what we were asking about. Trends in the periodic table.